Hello guys, this is Abhijit and today we will do lecture 2 part 1 of our classical mechanics. In the lecture 1 I gave you a short review about the Newtonian mechanics and the plus 2 stuff and little bit more intuition about the mathematics and the equations. Here we will do the core BSc mathematics. Okay, so we'll actually do classical mechanics that you will study in your BSc, and the prerequisite is mentioned here. You need to follow the prerequisite before watching this video lecture. Okay, and so let me continue and start. So what is the difference between the classical mechanics that you studied in your plus 2 and the classical mechanics that you will be studying in your BSc, okay, in your undergraduate courses? The difference is, in the plus 2 what you did is you looked at some equations, you understood the equations and you started applying it. Okay, and this BSc classical mechanics is all about looking at those equations mathematically. Okay, so a complete mathematics is involved. Now in this particular lecture you will learn one of the most valuable lesson of your entire life, corresponding to physics. Okay, so most valuable lesson. The lesson is, maximum time you don't have to go through the physical intuition to derive a result. All you need to do is look at the mathematics. This is the big lesson, okay, of theoretical physics. We are going to do theoretical physics, then this is the lesson that you must learn now, that most of the physical ideas are already encoded in the basic laws. You don't have to think again and again. I'll give you some example as we go forward. Okay, so remember this notation. I have already discussed a lot of times. These things just make things short. Like r dot is dr by dt. So wherever you see anything with a dot, it is a derivative with respect to t. Okay. So example number 1. Okay. In this example, I'm going to describe how the basic mathematical formula contains the physical meaning, or the physical things that you are going to see in a particular derivation. Okay, for example, you know that when something moves under gravity, the angular momentum is 0 because the torque is 0. Okay, this is what they say, this is what you know. Okay, so you might have studied this in your plus 2, but question is, where is this information encoded? Okay, where is this information that the angular momentum is conserved, is encoded? Well, let me tell you, the equation is actually encoded in the formula for gravitational force itself. Yeah, this is true. Okay, you don't have to go through much of intuition, neither you have to go through much of what happens and what doesn't happen, and you don't have to go through anything. Just one thing that contains this information is the equation for gravitational force, and now I'll prove you mathematically how this equation contains the information that angular momentum is conserved, and that is, in any central force motion, the angular momentum is conserved. Now what do you mean by central force motion? Okay, so let this be the sun, okay, and let this be the earth. Okay, so the force between sun and earth acts in this direction, in the radial direction towards the sun. So what do you mean by radial direction? You join a line from the sun to the earth. Okay, that's the radius. The radial direction is nothing but the direction in the radius. Yeah. Okay, that's why it is called radial direction. It comes from the term radius. Okay, so what is the nature of our gravitational force? The nature of this force is, it is acting towards radial direction, and hence I have written this force as a function of r. Okay, now question is, how does it depend on radius? Okay, it depends like 1 by r square. It depends like 1 by r square. Now question is, does all radial force depend on r like 1 by r square? No, there are some radial forces that depend on r directly. Okay, the best example is, remember this formula, F is equals to m v square by r. Okay, so remember this is the formula for centrifugal force. Okay, so when an object moves under centrifugal force in 2D, so consider I have an object and the object is like this. Okay, and say the object is going to move in circular motion. Okay, so when the object is going to move in circular motion, we know that there is a force that pushes the object in this direction, and this force we call it as centrifugal force. Okay, so this centrifugal force is directly depends upon r. Well, it is actually false to say that centrifugal force is inversely proportional to r. Do you know why? The reason is the velocity is itself a function of r. Okay, the velocity is itself a function of r, so you cannot say that it depends inversely. You have to write everything constant and r. Okay, so you have to make everything constant. For example, let me turn this velocity into r omega. Okay, so if I turn this velocity into r omega, then v square becomes m, it is r square, and then omega square and then r. Okay, so this will fetch me m omega square r. Okay, this will fetch me m omega square r. Let us try to understand this. Here m is constant and omega is constant. Okay, so both m and omega square is constant, so I don't need to bother because everything is constant. And now I can write that my centrifugal force is directly proportional to r. That my centrifugal force is directly proportional to r. So there are various examples of central forces. This is also an example of central force in 2 dimension. Please remember, this is the motion that you do, circular motion is actually all, these are all 2D stuff. Okay, I hope you remember these are all 2D stuff. Now continuing with our discussion with 3D forces. Okay, so a best example of 3D central force is gravitation. You see the force is 1 by r square. There is a reason why it is 1 by r square. In 2D the central forces are always in terms of r. Please remember this. And in 3D the central forces are always in terms of r square. There is a particular theoretical reason. Okay, I'll give you later on. Okay, let me give you a hint. You see, think of flux. Okay, when you look at the electric force, okay, the flux that comes out of the electric force, they go on decreasing in terms of the area of the sphere. Okay, so if you have a bigger sphere, then the area will depend upon the radius, that is 4 pi r square, and the flux will also decrease. I mean, flux is electric field lines per unit area, so the flux decreases as we go to the bigger spheres, and the decrease goes like r square. You will understand this later on when you study the electrodynamics. Okay, so we are discussing central forces in 3D. We are discussing central forces in 3D. Let us concentrate. So my aim is to prove to you that the angular momentum is conserved. That information is encoded in this one formula. Let us see how. Okay, let us try to derive this formula torque. Okay, I don't mean derive this formula, we'll use this formula actually. So torque is r cross f. Agreed? Torque is r cross f. Now we know that torque is rate of change of angular momentum, and we know that force is d by dt of p, that is rate of change of momentum. Since r is constant, momentum is constant, so d by dt comes outside. Sorry, since r is constant, d by dt will come outside. Okay, now this rate of change of angular momentum, okay, here we in this side, in the right hand side, we have applied the product rule. Now you would say that if I said r is constant, Why am I taking dr by dt? If r is constant, why I am taking dr by dt? Well, truthfully, r is not constant always. Okay, in circular motion, r is constant, that you have seen in 2D. But when we look at the motion in terms of gravitational force, you see there's an elliptical motion. So the r is not constant. So r also changes with time. So it is valid to apply product rule. It is valid to apply product rule. You must apply product rule. Okay. So after applying product rule, you get this. Now what is dr by dt? Now dr by dt is the velocity. Agreed? Dr by dt is velocity. Now what type of velocity it is? It is the radial velocity. Okay. And r cross, you get dp by dt in the right hand side. This is nothing but force. Agreed? Now since these two v are in same direction, this term is 0. Agreed? And r and f are in same direction. How r and f is in same direction? You see, this is r and this is f. They're actually parallel. The r and f are actually parallel to each other, not in same directions, opposite, but they are parallel to each other. That's what we need. And we know that two parallel vector, their cross product is 0. This is cross product 0 and this part also has cross product 0. So both the terms we get 0. So dl by dt is 0 mathematically. Please understand this. dl by dt is 0 mathematically. The only reason it is 0 because our f is a function of r, and since f is a function of r, the r cross fr is 0. Agreed? And as a result of which we get rate of change of angular momentum is 0. So I actually mathematically derived the result that angular momentum is 0 under central forces. Okay, you don't have to use your imagination or intuition. Just by doing some mathematical steps, you can actually come to these conclusions. This is the most important thing that you need to understand in your undergraduate physics. And most of the classical mechanics that you learn in your BSc is mathematics. You look at Lagrangian equation of motion, you look at Hamiltonian equation of motion. Okay, these are all some mathematical terms. Now, why is like that? Why it is like that? Why do we do mathematics? Well, please try to understand the classical mechanics that you studied in your plus 2 using so-called intuition. Okay, things are not intuitive, truthfully. Things are mathematics. Things are more mathematical. For example, when you ask a plus 2 student what governs the classical mechanics, they would say that okay, the forces, the velocities, the acceleration, they govern the classical mechanics. But when you go and ask the BSc student what actually governs the classical mechanics, you'll say the Lagrangian equation of motion governs the classical mechanics. And it is truth. It's a truth. The Lagrangian equation of motion is some non-intuitive equation that actually governs our world. You see, our world is made with clear mathematics. As you go and you study higher physics, like you go into quantum mechanics and string theory and other theories like this, you'll understand this world is made in more mathematical way than in an intuitive world. Okay, till a particular age you see everything is intuitive, but after that it is mathematics. It is actually done in a mathematical way. Let me give you some side information. Please search for Fibonacci series and please read about it. It's a quite very interesting thing, and I won't discuss it in this class, but I would suggest you. The name is Fibonacci series. Okay, first discovered by Leonardo da Vinci. Okay, let us go for another example. Remember kinetic energy that we discussed, and we derived kinetic energy in a very clever way. I hope you remember the derivation. If not, you go to lecture 1 part A, you will get the derivation at the end of the lecture. Okay, so this term kinetic energy, what I want to prove you in this particular example too is the term kinetic energy is mathematically obvious and it is already encoded in the work done. So you have not discovered kinetic energy as a separate term. Oh my god, it's 1/2 of mv square, some kind of kinetic energy, and that results from work energy theorem. It's not like that. The very definition of work done, that is work is equals to force into displacement, it holds the key, or it holds the kinetic energy within itself. Okay, let us look at the derivation. Let us look at the derivation. Let us look at this particular derivation. So what do you mean by W12? So W12 is work is done in taking an object from 1 to 2. Okay, so what is the total work done? It will be integration of f dot dr. So when you do integration from 1 to 2, you are actually dragging the object from 1 to 2. Now why do you do the integration? Yes, sometimes the force is changing with r. You need to do the integration. Always the force is not constant. Now if the force is constant, you can happily write work is equals to force into displacement only if the force is constant and the force is not changing with distance. Okay, but the moment as is displacement. Okay, the moment the force is changing, okay, you cannot write like this. You cannot write like this. The total work will be integration of f with ds. Okay, and here whenever I write in this form, please remember that f is a function of s. I mean f is a function of distance. Okay, the moment f is a function of distance, what is the meaning of f is a function of distance? It means you are dealing with changing force. Straightforward, it means you are dealing with changing force. So whenever you might have done problems like this in your plus 2, whenever you deal with changing force and you are asked to find something, all you have to do is integrate it, because you can take the forces constant in small parts and you go on adding. I hope you know what integration means. Okay, so work done is f dot dr integration. Now mathematically this force can be written as rate of change of momentum. That has been written here. Okay, that has been written clearly here. Now once you write force as rate of change of momentum, momentum can be in turn written as mass into velocity. Now velocity is r dot. Remember I discussed in the starting of the lecture that we are going to use this notation. Whenever there is a velocity, it is rate of change of distance. Okay, and it is velocity. So anything with a dot, any object with the dot is rate of change with respect to time, and if it is distance, then obviously rate of change of distance with respect to time is velocity. So the momentum here is written in terms of velocity. Okay, r dot means velocity. Okay, now what is dr? Okay, what is dr? So d dr, okay, can be very cleverly written as, how about I write a dt here, okay, and a dt here. Is there any problem? No, the 2dt will get cancelled and you will get r. So actually I can write dr in this form. Okay, and what is dr by dt? It is nothing but r dot, as we have discussed, and it is dt. So what is dr? Dr is r dot dt. So why do we write this in this fancy manner? Well, as I said, we are trying to derive something very mathematically. Okay, so we are writing this in a fancy manner, and going to the PDF, what do we get? We get d by dt of m r dot. This was quite clear, and then we have r dot dt, and then we have r dot dt. Okay, so please understand, this r dot is outside this differentiation. Okay, again I'm repeating, this r dot is outside this differentiation. So take r dot inside. What I have to do, I take differentiation of this term. Okay, the moment I differentiate this term, I get this, because half m will come outside. D by dt of r dot will be 2, okay, 2 r dot. Okay, the 2 will get cancelled and you get this. Now what is half m r dot square? What is half m r dot square? R dot square is velocity square, that is energy. So what mathematics you get? Integration of differentiation of t is my kinetic energy. Okay, this is what is used in most of the terminology in BSc books. I am using t. I could have written Ke, that kinetic energy that you have read in your plus 2, but in most of the books it is written as T, so I have written this notation. So what is integration of differentiation? It's nothing, they cancel each other. Okay, all you have to do is put the limits in this kinetic energy. So what do you get now? You get T2 minus T1. So what is the meaning of T2 minus T1? It means if you do a work and you move an object from 1 to 2, then the object gains certain amount of kinetic energy, and that kinetic energy is initial kinetic energy minus final. Okay, let me explain you diagrammatically. So consider there is a ball. Oops, it is not a ball. Yeah, this is a ball. Consider there is a ball. Okay, and what you do is you apply a force on the ball and you do a particular amount of work. Okay, now say initially the ball had some kinetic energy T1. Okay, initially this T1 is not coming from this F. Okay, this T1 is not coming from this F. So now what the F does, now what you do is the F moves this ball. Okay, the F moves this ball till a particular distance S, okay. So now the ball reaches here. Now our ball reaches here. So when the ball is here, this work done F dot ds, as I've discussed earlier, so what does the work done do? It will impart some energy. And now the ball here has a kinetic energy which is equivalent to T2. Okay, now can you tell me how much of energy is imparted by this work done? Okay, the energy that is imparted by this work done is equals to the change in kinetic energy of the ball. Okay, so what is the change in kinetic energy of the ball? It is nothing but the final kinetic energy minus the initially possessed kinetic energy. Okay, most of the time when you take the object at rest, if the object is at rest, most of the time when you take physics problems, you assume the object is at rest. So if you assume the object is at rest, then T1 can go to 0. Okay, so what I mean to say here is the term. So what is kinetic energy term? Half mv square. Okay, so why it is half mv square? It could have been half mv. Why not half mv cube? It cannot be like that. You are not the person who defines kinetic energy. The kinetic energy term is mathematically included in the work done. Okay, I hope you understand what I'm trying to say. In these two example, what I depicted is most of the time the physical intuition is already there in the mathematical stuff. Here as I discussed, that the conservation of angular momentum in central force motion is already encoded in the force itself. Okay, so question is, I hope you understand this mathematics. Okay, what I'm trying to explain you here. And now we'll go to some notations. So why I'm teaching these notations, because when you open your some standard books of classical mechanics like Goldstein and Greiner, what you see is it is filled with notation of these types. Okay, so my work here is, let me explain you what is the meaning of these notations so that you feel easy when you go through those books. Okay, so notation number 1 is summation actually sums. Okay, summation actually sums. So when I write summation over I, so the I goes from 1 to 3. So actually 1 plus 2 plus 3 can be easily written as summation I 1 to 3 I. Okay, so instead of writing 1 plus 2 plus 3, I can write this small term. Okay, sometimes it can be 1 plus 2 plus 3 plus dot 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 10. Instead of writing that much big term, I can make a small notation. So this is nothing but a notation for convenience. Like instead of writing dr by dt again and again in the derivation, what we do is we write r dot. Okay, similarly, instead of writing the sums, what we do is we make a notation for that. Similarly, if there is a n addition, then what you do is you write I goes from 1 to n. Okay, so this is the notation. Now so consider there is an object, okay, and it is acted by n number of forces. So you are not seeing here n number of lines, I have omitted it, but this each dotted line is a force. Okay, so there is a force F1, there is a force F2, and there is a force here in this direction F3, there is a force F4, F5, F6, F7, F8, dot 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 dot, there are Fn forces. So how to write the resultant force? Obviously the resultant force is a vector sum of all the n forces. The resultant force is going to be a vector sum of all the n forces. So it's gonna be written like this. So you have to vector sum of all forces. Now please understand, this is a vector sum, it's not a scalar sum. So if this is 10 Newton, this is 10 Newton, this is 10 Newton, everything is 10 Newton, you don't go on writing 10 plus 10 plus 10 and you go on adding the 10. No, it is not scalar addition that you will go on adding like numbers. You have to look at the direction. Okay, you have to add these two first, then whatever resultant you will get, then you have to add it with F3. This is already there in your plus 2. Okay, so this is a notation that I am trying to say, that I can write total force in this manner. I can write total force in this manner. So it will become a summation I goes from 1 to n Fi. Okay, so I think it's written J by mistake, so it should be I goes from 1 to n. Okay, the same notation as this. So this is second notation. Third, you will see your book filled with position vectors. Okay, so let me explain you what is the meaning of this position vector. See, whenever you do a physics, you need a background. For example, when you do classical mechanics, you do classical mechanics in coordinate system. Okay, so you cannot think of classical mechanics without coordinate system. Okay, you try thinking classical mechanics without coordinate system. Any problem you do in classical mechanics, you always think of coordinate system. So the basic background of classical mechanics is coordinate system. Similarly, when you go to quantum mechanics, the basic background is linear vector spaces. Okay, linear vector space is the basic background upon which the quantum mechanics is standing. Okay, so that's why we study coordinate in details. We study the coordinate system in details. So in classical mechanics, what they do is, any point or any object in the say xy coordinate axis can be represented by a vector r from the origin, and this r is the position vector, because it defines what is the distance of this point from the origin. Okay, it defines what is the distance of this point from the origin. That's why it is called a position vector. Now say the object takes a complicated motion. Okay, let me give you one simple motion. Say this is my y-axis and this is my x-axis. Okay, let me label them. So this is my y-axis and this is my x-axis. Now consider here is my object. Okay, say the name of the object is P, and say the position vector of the object is given by this. Okay, so the position vector is given by this. Now, so what is this? This is r. Okay, this is my r. Okay, now imagine this particle goes straight in this direction. So when I say the particle is going in this direction, I mean the x is only changing and the y is same. Okay, I mean to say that x is only changing and y is same. Say the y is 3. Okay, y can be any number. So when the object is moving parallel to x-axis and there is no change in y, can you tell me how is this position vector changing? You can see that initially the particle is here. Okay, it is represented by r. At another time the particle is somewhere here. At another time the particle is somewhere here, and say this is represented by r dash. Okay, so now say in the third time, again in the other time the particle is somewhere here. Okay, so what would be the position vector? The position vector will be r double dash. Okay, so you see that for a moving particle, for a moving particle, the position vector r can be a function of time. The position vector r can be a function of time, and since the r is changing with time, so I can write that the position vector of r is changing with time, and r dot will give me the velocity, or r dot will give me, okay, so what is r dot? It is, as I discussed earlier, dr by dt. Now I can have another definition attached to this. So if I have dr by dt, I mean to say that r is changing with time, and dr by dt is the mathematics that tells you how the length of r is changing with time. You see, the length is changing. Here the length is here the length is something, here the length is something, here the length is something else, okay, and basically the length is increasing. So dr by dt must be a positive change, okay. So dr by dt must be a positive change because the length is changing. So I hope you understand this thing about position vector. The position vector only defines how where the object is. The position vector only defines where the object is, okay. So let us move forward to other notations, okay. So here I have given another complicated motion. So instead of initially here I assume that the particle is moving in a straight line parallel to x-axis, okay. So y is not changing, only x is changing, okay. So if r is a function of x and y, the y is gonna stay constant, and there is a constant change in r with respect to x. So here both r and here the r is changing with time because the particle is moving, but you see that x and y both are changing, x and y both are changing. So here also r is a function of t, and nothing different, okay. So this is second notation, okay. Third notation is position vector. When two position vectors are given, you can find the distance between them, that is called as displacement vector. Now it is called displacement vector. So consider a particle was initially at p, and then the particle moves to q, okay. So as discussed earlier, when the particle is moving from one point to another point, the radius vector is changing, okay. The radius vector is changing. Similarly, if the particle moves from p to q, so if the particle is moving from p to q, the radius vector has changed. So initially the radius vector was r1, now the radius vector is r2. Now if the question is asked by what distance this point or this particle at p moved to q, by what distance, okay. So you have to actually apply geometry, yeah. You just cannot do, say if r2 is 2 centimeter and r1 is 1 centimeter, you cannot do 2 minus 1, that is 1 centimeter. This is not a scalar, remember these are all vector quantities. So either you use the geometry of vector, or you draw the diagram and use a scale to find these values, okay. So whenever two position vectors are given, you can find the distance between the tips of two position vector, and the vector representation is r2 vector minus r1 vector. But when you convert this into magnitude, things are going to be complicated, and that complicacy can be solved from geometry, okay. So these are all the basic notations that you will find in your classical mechanics book. Is nothing great. In lecture 2 part B, we will continue discussing some more notations, like how the potential between two particles is defined, okay. If there is a ith particle, so consider an n particle system. If there is any ith particle and there is any jth particle, then how to write the potential, how to mention the forces, okay. If I mean the internal forces, okay. Then what happens when the object moves, what happens to the center of mass, we will all discuss in the lecture 2 part B, okay. Stay tuned for this lecture and have a nice day. Thank you for listening to. Okay, bye.